strong formulation, or solution to the strong problem, I guess, proves that this implies the strong formulation. Okay. We start with integration by parts again, because we, to throw the derivative back on the u. 1, 3. U. Oh, I'm looking at the wrong. d2u dx squared v dx. So the integration by parts applied to this first term here again. Cost the bounded term again, of course. So here goes du dx v 1, 3. And then we still had this bounded term in the weak formulation. Okay. And this is equivalent to using again the boundary condition on the v here. You can write and multiplying everything by -1. We get d2u dx squared v dx plus, then combining these two terms into this, du dx -2, and then v, and all of that evaluated at x equals 1. Because I've applied the boundary condition since v3 equals 0. I've used that. Okay. Now comes the trick. Because this must hold for all v, so we can take a particular choice. As v is arbitrary, choose the following. Take this v. V equals some function psi of x, which I'll say what it is, times the second derivative of u. Okay, where, what do we choose for this psi function? It's psi of x equals 0 at x equals 1, positive in the interior domain from 1 to 3, and 0 again at x equals 3, as it must be, because v must satisfy the, so note now, note, because of this, v3 equals 0, as we can choose, according to the weak formulation rule. Okay, and it's not difficult, of course, to write down a function like this. It's something like a bump function, something like that, right? Such functions certainly exist. And with that function, we can now insert this v as constructed here into that equation. Then 1 to 3 of psi x integrated against d2 u dx squared dx equals 0. And this was the whole purpose of this form. This was intentionally taken to be 0 at x equals 1, so that this term here vanishes. Okay? And we're left with this, and we have a square here, so for this to be 0, the second derivative must be 0. Okay, so that was the whole game here, of course. So this means that for this to be 0 for all psi, you can still say, okay, it must mean that d2u dx squared equals 0 for x between 1 and 3. Okay, that's already the equation of the strong formulation and the boundary conditions. But once this is 0, then we go back to this equation. Let's give it a name, star, and we can say that then from star that means that this integrand is 0, this integral is 0 here, and so it means that this must be 0. So then we have that du dx minus 2v, all of that evaluated at x equals 1 must be 0, for all v such that v3 equals 0. Okay, so we can again take a special v, and that's easy enough here. We take one where v is 1 at 1, for instance. Then we get rid of v there. So now take v such that v at 1 equals 1. And we still have, of course, also that v at 3 equals 0. So it's easy enough to construct such a function. A straight line would do, for instance, but we don't need to get into that detail here. But let's say, for instance, a straight line between 0 and 1. Just to confirm that there is indeed such a function. So now take that as that. Then du dx at x equals 1 equals 2, which is exactly the boundary condition of the strong formulation that we started with here. And this one is still carried along. This was not touched. So we still had that as well. We still have that as well. We also, because that was part of the explicitly part of the weak formulation too. We also still have u3 equals 1, and so we have the strong formulation. Weak implies strong. QED. Okay, so that's how you can do this, and I think it's clear from this that you could do this in any example. Really, there's nothing special about this problem. Okay. I agree. This feels like cheating here a bit, but read it carefully, and you see that it checks. Okay. Let me